Yeah, that.
So funny.
Hi everyone. So I'll be talking about the work that I've done this summer with Mike specifically. We're working on making a floating point a sampler for continuous Gaussian distributions, specifically during the noise addition step. Before going into some details about the sampler itself, I wanted to bring up some of the risks that come up with floating point arithmetic. This is what Amit was alluding to in his talk with the privacy leakage risks that comes with some floating point operations. But essentially, for floating points themselves, their representative values are not uniformly spaced. And the spacing, which is based on the last mantissa bit, or the unit of last precision, within any binod, so any consecutive power of 2 is constant, but when you move up to higher consecutive binods, then the spacing actually doubles. And because that spacing differs between these binods, if you do any kind of floating point operation whose output lands on a different binod than its input, this can create some data-dependent artifacts as a result. So an example of that are holes, which is when you have an output that is reachable from one input, but is not reachable from its neighbor. And because of that, if an adversary can observe an output, it can potentially infer what that input is. So there are some concerns there. For the sampling methods, in the beginning of the summer, for the first presentation that I had, Mike and I were actually looking at another approach called mantissa bit manipulation. And this helps with repairing the mantissa bits for that final release value. So this can be helpful if, say, denormalization that causes trailing zeros at the end can happen, or for any kind of rounding rules, if that may result in some biasing of the last bit. Repairing those last mantissa bits can help, but this will only really address the noise addition step. If there's any kind of operations that happen prior to that, that can't really be addressed with this approach. Naively, what one can do when producing this float that results from multiplying that scale, which is the sigma value, by the standard normal, and then adding the location mu, what can be done is building that output through inexact floating point operations, which is what has been done previously and also with MBM, and then casting that value, rounding it to a float. With the rounded Gaussian sampler approach that Mike has, this is a way to represent that exact noise as partially revealed, so not revealing all of the precision for the bits, and then certifying that it fits within a float cell. So we can do this with a rejection-based sampling method called Carney's method, basically running Bernoulli trials, and within each trial doing some lazy comparisons between bits, and then from there proving that the value falls within a cell using exact integer operations. That's for one version of an algorithm. For the other version, you can actually compute the value using exact integer arithmetic. And for both of these approaches, in no step are you doing any kind of inexact floating point operations, which would lead to some of the concerns that we talked about previously. This is the algorithm overview. This is the same one that I talked about in the midway presentation. Hopefully you can see the text is a bit small, but in this first part, this is producing the trace itself. So we're sampling first the integer part from the discrete half Gaussian, and then sampling the fractional part. If it's rejected, then you restart, and then the ideal output would be an accepted trace with those components. And then from here, for this version of the algorithm, it has certification. So with that interval that is created from the trace that was produced from the prior step, you would take the midpoint of that, and that would function as your candidate hint or your guess. And then From there, you would certify if that interval lies between a float cell itself. And if in the case you are not able to certify, like within the given budget that you have, which is for this version of the algorithm around 96 bits, then you would have to completely restart with a fresh new trace. So this rejection part for this part of the algorithm is called comb rejection. But there is another version of the algorithm that Mike has that doesn't have this comb rejection part. So we can expect this algorithm to be a bit more efficient than the comb version, just because during the finalization steps, there's no rejection sampling, no rejection loop happening there. And we can do that by representing those values as coordinates on a dyadic grid and then doing some exact integer addition in the end. Also, another version of this algorithm that Mike was exploring was using a base 2 version. So instead of sampling from the standard discrete Gaussian, you can sample from the binary Gaussian. But to do this, there is this snap up requirement. So that A value right there is the noise multiplier. But for this algorithm overall, we can also expect it to be more efficient than when we were using the base E Carney sampling, just because there are less comparisons that are being made. So for example, when we're sampling K, that integer portion, we're not running any kinds of Bernoulli trials or any kinds of integer comparisons between them. We can sample it from fair bits. So because there is no comparisons happening at that part, and overall this can lead to lower branch divergence, which can potentially lead to faster execution time. And actually in some of the benchmarks, which I will be showing later, this base 2 approach did actually have some faster runtimes compared to the base E approaches with Carney sampling. And also, if anyone has any questions or comments throughout, please feel free to interrupt at any time. And then in terms of the actual implementation with this algorithm, the main goal for this first is to support some large repeated releases, ideally targeting private machine learning model training, which Eddie has been helping out with benchmarking on some models. And because we're doing a lot of repeated work here, the easiest way to make this a lot faster, because ideally we want to generate many samples at once for training, is to parallelize this and have independent samples be generated. And initially, I was exploring assigning one CUDA thread per sample. And I'll talk about some other approaches that I was looking into for this part of the design later on. And in terms of the randomness source as well, first we were experimentally using a counter-based generator that was native to CUDA itself, and it can generate independent entropy for all of the individual threads. And then we were looking into adapting a cryptographically secure version of that generator from Torch. So in terms of the, first I want to talk about some of the attempted improvements I tried to make, but unfortunately either kept the execution time the same or slightly worsened it. So unfortunately all of these efforts, which have taken a lot of time, did not really amount to anything, but I think these are good lessons to take into account too when we're thinking about optimizing with CUDA. So first, I talked about in the last slide how I first wanted to have one thread be assigned for one slot. So a slot is an attempt that the producer makes. But the problem with this is that some threads might take a lower amount of time to execute, and because there are 32 threads in a warp, and for a warp to execute, it would need to wait for all of the threads within it to finish before it's able to complete. If you have a thread that finishes faster, then it would have to sit idle and wait for the other threads in its warp to complete. So there's that idleness inefficiency. So one of the approaches that I was thinking about to address this is using this work queue model. So you basically have this counter that is held in global memory that's able to allocate slots to different threads. So anytime a thread requests for more work, it's able to get a chunk of slots to work on, and once it finishes those chunks of slots, it would go back to the counter and request for more. So in that way, no thread is being left idle if it finishes work early. And instead of the one thread per slot approach, where after the thread finishes the work with its slot, it would immediately exit. In this case, all of the threads would only exit when all the work is done. So in that way, ideally, all of these threads could finish at the same time. However, this actually made the algorithm a bit slower than what was originally benchmarked. And I did forget to mention this, but one of the first designs that we made was splitting the producer part, so producing the trace itself, and then finalizing the trace, splitting those into two different kernels. And the reason is because the first kernel, which does the producing of the trace, that one has a lot of potential divergent branches that come from the unbounded loops from the rejection-based sampling, whereas the finalizer kernel has mostly constant time work because there's less of those unbounded loops. So we decided to separate those. Actually, I missed this slide, but over here we can see that this single approach, which is putting the producer and finalizer into a single kernel, that was a lot slower than if we were to split the producer part and the finalizer part into their own separate kernels, and it was around like a 2.8 times slower from there. Also, with this approach, it reduces the register pressure as well. So we can see that with the split approach, the producer and the finalizer each had less registers per thread compared to the single approach. But this is at the cost of more global reads and writes from the finalizer, because after a trace is completed, then the data for that trace has to be stored within global memory, and then the finalizer needs to read those values from global memory. But overall, the split approach did contribute to much faster runtime. But going back to some of the approaches that I originally experimented with, the reason why that work queue model didn't work out that well with the global counter was actually because the global counter added quite a bit of overhead with all of the addition happening in global memory. And there's also a final read. Once the threads finish all the work, they need to verify that all the work is done, so they would have to have a final read from that global counter. All of that contributed to a lot of overhead and made the kernel, unfortunately, slower than the originally benchmarked approach. Another approach was to get rid of this global counter and instead just statically assign different slots, consecutive slots per thread. But actually, this led to negligible improvements in the benchmarking, just because some of the logic there had this overhead with a loop that was written and actually serialized a lot of the work that was being done. So that didn't really work out well. And then from there, I was thinking, okay, surely if I try to reduce the number of instructions or reduce the number of live registers, that would improve the runtime. That is the case for CPU-based logic, but unfortunately not always the case when we're thinking in terms of the GPU. So for example, I tried an experiment for reducing the number of instructions that were happening per thread during the refining part of a loop, and actually reducing it by 9 times. So the original implementation had around 900 instructions, and that was because so many calls were being made to continue refining, which is adding 4 more bits. And I tried reducing that logic to around 100 instructions, but that led for the kernel time to be largely unchanged. And that is because the kernel is unfortunately latency bound, meaning that for a given clock cycle, most of the time the warp is not ready to be executed. So here I'm targeting a different concern when the main bottleneck is that the warps are imbalanced and some are ready to execute while others are not. In addition to that, I tried to reduce the number of allocated registers, so the number of values that were live at a time for a function that did the lazy comparisons. And it made the execution time a little bit slower, and that was because even though I was able to reduce the number of registers for that particular function by around half, I, in the logic, accidentally created a divergent branch because of an early exit condition, and because of that divergent branch, that dominated any kinds of time that was saved by less registers being used. So unfortunately, when just the main takeaway when programming with CUDA on GPUs, all of these considerations need to be kept in mind, and sometimes things that seem like intuitive to implement within the CPU may not necessarily be true on the GPU, unfortunately. And for all of these approaches overall, these reduce even though they reduce the costs on the register side and on the instruction side, because this was only happening on the divergent branch of the kernel execution, which is when those threads are idle, it didn't really amount to any kinds of changes happening with the total runtime because it wasn't addressing the actual bottleneck, which was the warp imbalance. And some of the observations after I did those experiments were to look at the imbalances happening per warp. I came to discover that only 2 out of 32 threads per warp were active at a time, which is quite low occupancy. And if we're looking at the overhead factor, so we can take the ratio of the maximum time it takes for a thread within a warp to execute over the average workload for a thread to execute. If we take that ratio and, for example, looking at some of these metrics like how many times it took for the comparisons during the lazy comparisons rounds to complete, how many times we had to do the refining for the lazy comparisons, or even how many times we had to invoke the Bernoulli sums. All of that was around taking like 3.6 times as long as if we were to assume a perfectly balanced situation, and that assuming that all threads would take the same amount of time. And for these particular steps, which is part of the Carney sampling, the average amount of idle threads at a time was around 70%. So improvements should be targeted towards those steps specifically. In addition to the producer attempts as well, it was around 60%, which is not ideal. So from here, it would be best to focus in optimizing in these particular areas within the algorithm. And for the comparison rounds, that was actually helped by the base 2 Carney approach that I mentioned earlier, because less comparison rounds were being used than the original approach. And for the producer attempts, I actually addressed that with an approach that we were talking about during during the midway presentation that we had a couple of weeks ago. So basically, each thread would just run one attempt and mark that attempt as a rejected trace or an accepted trace. And then from there, the finalizer would just take the accepted trace only. And that way, you're only bounded by the longest time it would take for a single attempt to happen, rather than waiting for all of the retries that are happening with having multiple attempts. So that improved runtime quite a bit from this last row over here.
Can you say what single attempt is again?
Single attempt is this is the producer attempt that I mentioned. So that's when each thread runs one attempt, and then only it would mark if that attempt was accepted or rejected, and then a finalizer takes just the accepted ones. Yeah. And also these were with the non-cryptographically secure generator that was built into CUDA. I also tried benchmarking this with the torch-adapted CSPRNG version, which did amount to slower runtime as expected. But I did try to make some improvements on top of the torch-adapted one. So this one is AES based, and originally the lookup table was stored in constant memory, but it could be parallelized by doing a global read from a data cache if you were to store the lookup table there, which actually made it a bit faster. And then also, if we keep the cipher state and the work that comes from the rounds when we're using the CSPRNG, if we keep those stored in registers as opposed to memory itself, and not having to do those slow memory accesses, that would also help with runtime, as we can see with the last row over there with those AES improvements. So overall, this is all the work that's been done so far with the algorithm itself, and with the little optimizations that we tried to make. And I think that we are on the, oh yeah, go ahead, Mike.
Am I seeing that this is on the last row, the performance degradation is basically just 4 times baseline inverse CDF?
Yes, so actually I was surprised about the baseline inverse CDF because 4 milliseconds seems quite long compared to the baseline inverse CDF from the non-cryptographically secure version. So I may need to redo the benchmark for that, but I was seeing that it was, approximately 4 times as fast.
Is that with the baseline inverse CDF also using the AES from torch?
Yes, exactly.
Okay.
Yeah.
That makes
Mm-hmm.
sense.
So there was a concern that I saw because in the last one, this is with the non-cryptographically secure, so the Philox one, that was around like 0.05 milliseconds, and this one was like 4.5, which was quite a difference. So I wanted to redo some of the benchmarks there, but overall, in having this AES-based one, the fastest approach that was benchmarked so far was using the base 2 Carney, the single attempt approach where the producer just does 1 attempt per thread, and then having some of these AES improvements in relation to just the memory optimizations. So that version had the fastest time so far.
And what's the delta with or without AES for like base 2 Carney? It's 27 on this here.
This is with the...
No, on this one they're all with AES, but what's the delta with or without AES?
Oh, I didn't include that in this presentation, but I think it was around like twice as, or around like half the runtime for this version of the AES. But I can share those benchmarks with you later.
Yeah.
But overall, like, I've had a lot of fun, and I learned quite a lot with how to optimize using the GPU. And it turned out that there were so many other headaches that I didn't really consider. So it was a great learning experience, and I appreciate everyone here. I enjoyed my summer, and I think I mentioned before that this was my first project that is relating to DP, so it was a very fun experience, and yeah, I appreciate all of you. Thank you.
really valuable work. It's really very informative for what we do going forward. So if I understand correctly, you're saying that we're having a big underutilization, this like 2 out of 32 on average of like potential parallelism that we're leaving on the table. Is everything you've been describing is for like generating a univariate Gaussian, like one number, like one
Yes.
right?
Yes.
In a block
So
of 32.
what?
In a block of 32.
What's it in a block of 32?
A warp. You're sampling 32 independent Gaussian variants at the same time. And in the warp, 2 of the 32 on average are active. The remaining 30 have already finished their samples.
Oh, interesting.
And you can't continue until the 2 have finished, until every single one is finished.
Great. And then some of the things that you've tried, like if we did more than 32 at a time, and would that is that included in the things that you were doing?
I didn't try doing more than 32 at a time. I tried an approach where it would complete the thread within, or complete the work that's required for that thread within the warp, and then try to pick up some other work that is independent of the rest of the threads.
That was the thing where the atomic counter was the bottleneck, and I guess that would also be a bottleneck if we tried to do more than 32 dimensions of the Gaussian at once. We would still run into that same bottleneck. Would that be the guess?
You're dealing with the straggler effect, so basically you're more likely to have like worse stragglers. I think sometimes it's usually there's like an optimum where it's like the stragglers on average are like this much, and as you get bigger, there's more likelihood of a longer straggler, if you will. Sometimes, so it's like there's like a number usually that like you have less for like these sort of pipeline jobs, like Spark and all these systems try to deal with it, where effectively like the straggler effect is variable to, so 32 has, it seems like 2 stragglers and 64 might have 4, and like you don't know how long they'll take sometimes, but that is something that can be like
yeah. But I'm saying like if we like maybe
you could do quantiles, like you could just take the first 32 to finish when you run 40, right?
Like there is a way of there are ways that you deal with stragglers in this case. I don't know exactly specific to the GPU, but there's a lot of ways people do it. Quantiles is a good one.
Yeah, but wouldn't that bias the distribution?
That is my
It would
concern.
not, because the runtime is independent. Or wait, maybe it's not independent. Oh, that's the problem.
Yeah.
But what if we like said, okay, each thread in the warp is responsible for, because we're doing like, if we're doing like, you know, sizable models, is way more than 32 dimensions of Gaussian that we need to sample, right? Now
What is
the dimension?
What is?
So.
Yeah, I have no idea. How high do you want to scale this up in terms of
So-
samples you're trying to throw?
So I trained on a 900, I believe it was, a 900K model, so almost like a little under,
100,000 parameters, so
Yeah.
that's the dimension of the Gaussian.
So
Yeah.
you're drawing a Gaussian for each.
but we're drawing we're drawing, I don't know if it was it wasn't the full model being trained, it was only the lower layers, but the noise ended up being about like 20% increase in runtime at that scale with an older model. So the 4x here isn't a 4x of the whole job, because this is GPU based. It's like 4x of a layer of the job. So in the grand scheme of things, as the model gets bigger, the proportionality of this like changes over time. But it is not like a 4x overall. It's like 4x, but then if there's untrained parameters that you're not updating with Gaussian weights, and then they're being multiplied through, the average ends up not being like 4x doesn't mean 4x of the job. It was only a 20% increase for.
Right, but I guess so maybe following on it, so it's 100,000 parameters. Like if we assigned each thread generating 100 Gaussians rather than 1, wouldn't kind of law of large numbers kick in and that tend to balance out the amount of work that's done for each thread, or is that for some reason not?
The issue with GPUs is like you're setting up a printing press, if you will, and then you stamp it. So the caveat here is like if you have a straggler, you have it ready, but you can't stamp it. So like there's a level of like that's kind of what kind of makes this a little bit trickier, if that makes sense. So like you want a lot of them, and there is parallelization across these. So it's not just one 32 happening at a time. There's many batches of 32 happening at a time when I run it on the code. So your effect that you're asking for, they're not measuring it as much, but it is coming to the numbers where it's like we're effectively filling out as much space as we need for the model with batches of 32 stamps. So it's like each of those stamps is happening.
But I think Slill's saying.
You also do need to wait for them all to finish before you use them, right? Because the timing is not independent of the, as this is what Mike was saying. Like,
No, yeah, I know, but I just want to exploit, like if I do 100 of these in sequentially, that is going to be closer to 100 times the average time
yes.
it takes, rather than it is to the the maximum time, because of some things finish sooner, some take longer, and then blah blah.
What I'm saying is we're doing multiple at a time.
You're saying put multiple slots in one thread, right?
Yes.
And wouldn't that push the memory pressure up? Because now
I see.
Memory requirements are multiplied by.
Got it. So that pushes up a problem somewhere else. Got it.
It might give you.
I think what you're saying is if you have like more Gaussians you're sampling than you do cores on the GPU, then eventually each core will have multiple jobs that it has to iterate through, and then you'll get a law of large numbers, and it's the maximum of a bunch of like law of large numbers Gaussians, one for each core.
Yeah.
Right.
And we're not stamping one of these at a time. We're doing many of them in parallel too. So like there's like parallelization on top of the original. So we're not doing 32 at a time, even with this current method. We have like maybe 8 or 100 of these like happening in that same batch of the calculation. So it's like 32 is like an atomic unit within a also parallelized set of noise creation.
GPU runs multiple warps.
So I actually have a question.
Throughput on each warp is possible.
Yeah, we want them to be as optimized as possible.
It might be possible to get more throughput on one given warp by packing multiple slots per thread. I think you tested that, right?
Multiple slots, yes, but I had that first, the counter issue, and then the second one was trying to directly assign each thread to have multiple slots without the counter, but they were all consecutive slots. That made the runtime actually pretty similar to when we
didn't get an improvement.
We did not get an improvement from that.
Yeah.
And do you have a guess for why?
That might have been because when I had to write a loop for it to iterate over how many total slots there needed to be to have that work be finished. I'm suspecting that there was some kind of there was some kind of issues with that loop itself that I had to add that might have caused more instructions to have to execute, which then caused slower runtime. That's what I suspect, but
more register pressure.
Yes.
More
I did not.
Register pressure.
I did not directly measure the register pressure, but that could be.
I think it's like the number of warps that you can run is based on the number of registers that your kernel uses. So if your kernel is very greedy with the registers, then you can't run as many warps because each warp is consuming more space.
Got it.
So I have one more question. So right now, like, okay, you're generating a bunch of data, then you stamp it, and that's your output, right? So you need to wait for all of the data to come in and before you can package them. So there's a straggler effect. What if instead of having one like thing where you stamp the final data. What if you stamp each intermediate, like at each rejection step, you generate a bunch of things that are candidates for the rejection sampling. You stamp that set, and then you reject, and then you stamp. You could separate out the, and then that would actually let you just throw away stuff, because then it would be independent of the runtime. Because the only aspect of the runtime that it's not independent of is the number of rejection. Or sorry, it is independent of the number of rejection, like the number of rejection steps you took, because it's just like a conditioning thing. Does that make sense? I'm not didn't explain that super well,
But I'm wondering, maybe we should take that, I mean, if you have a quick response.
I just wanted to clarify, Walt, did you mean that you have different threads take up different work that is happening within the slot itself?
So the goal is to reduce the straggler effect. And my hypothesis is there isn't that much variance in just like kind of like constant time calculations in the GPU. So most of the straggler effect will come from different amounts of rejection sampling you need to do for each variable. You could correct me if that assumption's not right. But assuming it's right, then you could reduce the straggler effect by just coming up with a huge number of things and then filtering them with the rejection sampling all at once. And then you're not like only using one intermediate rejection thing for each. You have like a pipeline of intermediate states for each rejection step. But there might be log
Maybe we
confusion.
should take it, let's take it offline just because we're running
Okay.
far behind schedule.
Yeah.
Can I make a quick comment? I think that this is single attempt. This is compaction. You could potentially do the same at all other pipeline stages, but the biggest win feels like it's at the first kernel, and I think that's what she did for a single attempt.
All right, great work, Alice.
Okay.